So this is just an introduction to using ice charts. Typically we use ice charts just like in the second semester when we're doing equilibrium, buffered systems, things like that. But I wanted to teach you how to use ice charts for simple stoichiometry problems, which you already know how to do, so that when we get to the second semester, things are smoother because you're not learning two new things at once. And I actually use ice charts all the time on even just regular stoichiometry problems if they involve two or more parts. So here is an example that we worked in class. Basically, if we have 15 grams of oxygen gas combined with 11 grams of hydrogen gas, what mass of water can be formed and what mass of excess reactant remains? Now, obviously, we would, if this was a formal question, I'd be more clear that there was no water to begin with. It was an evacuated container. And since it says can be formed, we don't have to worry if there was 100% yield or not. It's theoretical, and so we are just figuring out the most that can be formed. But it is kind of a classic limiting reactant question. And so the first thing I'm going to do, some people call ice charts rice charts, because the first thing you want to do is write the equation of the balanced chemical equation of the reaction, which in this case, of course, is hydrogen gas, oxygen gas forming H2O gas. And I'm going to harp on you guys to include your states of matter in all of your balanced chemical equations, because that'll be super important later on. So here's our equation, and then we're going to, along the left-hand side here, we're going to write the letters I, C, and E. Now, I, C, and E typically stand for initial, change, and equilibrium. But since we're not talking about equilibrium yet, for now you can just call it end, E and D. So initial, change, and end. And the couple of things to note about ice charts. One of the most important things is units. You can't use grams in an ice chart. You can use moles, you can use pressure units, and you can use concentration units like molarity, but you can't use grams. And so what I always encourage students to do is in the top left-hand corner of my ice chart, I'm going to write the unit that I'm using to remind myself, because you're going to find that when we get into like buffered systems, you're going to have multiple ice charts, and some of them will be in moles and some of them will be in molar. And so it's clear, it's helpful to be clear what you're doing. And if you write it there, you don't have to keep writing it everywhere else in the chart. So I've got a mole ice chart that I'm going to make. And so I look at what the given information is and I say, okay, well, what is the initial number of moles of hydrogen? Well, they told me it was 11 grams, and of course hydrogen is H2, so converting to moles, I get 5.5. And by the way, just a quick parenthetical, this is just an introduction. I'm not going to worry about going and getting all 4 sig figs off of the periodic table that I get to use on the exam. You will be expected to do that, but you know that, and so I'm just going to include just 2 sig figs here. Because quite honestly, even if I used all 4 sig figs for my molar masses from the chart, since I only gave you 2 sig figs in the given information, I almost guarantee you that it ends up rounding off the same. So don't be lazy like I'm doing right now. Use the full molar mass off of the chart using all the sig figs, and then round it. But trust me, it's probably the same on a question like this. And again, this is primarily about learning ice charts. All right, so 5.5 moles of hydrogen we started with, and then we do the same thing with oxygen, and I determined that I had 0.47 moles of oxygen to start. And of course, since water was the product, and I said they would be more clear and say that it was a previously evacuated container, we don't start off with any product. In equilibrium, we might start off with product, but for right now, we're just going to turn reactants into products, and so the initial product is going to be 0. So I finished the initial line. I know how many moles of each reactant and product that I start off with. So now the next question is, who's limiting? Now, last year, when you didn't have ice charts, you probably did one of 2 things. You probably converted the number or the amount of hydrogen you had into water and the amount of oxygen you had into water and figured out who produced more or who produced less, or you compared the 2 reactants to each other. We're still going to do the same thing, but ice charts allow us to do it much faster. So I'm going to show the slow motion way from last year, and then I'm going to show you how you're going to use your ice chart to do it much quicker. So we start off with, we're going to convert moles of hydrogen into oxygen. I write 5.5 moles of hydrogen over 1. Of course, I want the moles of hydrogen to go away, so I'm going to put that on bottom in my next term. And then I want to convert it to moles of oxygen, so that goes on top. And then, of course, you learned last year that the numbers that go with those are the whole number ratios, the mole-to-mole ratio, which comes from the coefficients of the balanced chemical equation. So that means for every 1 mole of oxygen, I'm going to use 2 moles of hydrogen. So then when I plug that in my calculator, I find that that means 5.5 moles of hydrogen would react completely with 2.8 moles of oxygen. Now, right away, I can tell who's limiting, because in order for the hydrogen to completely react, I need 2.8 moles of oxygen, and I've already indicated that I only have 0.47 moles of oxygen. And so right away, I know that oxygen's a limiting reactant, and so I'm going to write that above oxygen in my ice chart to remind myself that that's the limiting. Now, I don't have to do this next step, obviously, because I know who's limiting, but just in case it were the other way around, I'm going to show you that if you had chosen to convert oxygen into hydrogen, you'd still get the same information, right? So if I do oxygen, 0.47 moles of oxygen, use the coefficients to determine how much hydrogen that would require, I get that 0.47 moles of oxygen would want to completely react with 0.94 moles of hydrogen. Do we have enough hydrogen? Yes, we have 5.5. So we clearly have enough hydrogen, which again tells me that oxygen is limiting. All right, and then here's what I mentioned as being a shortcut. With ice charts, what we're going to do to compare, we're going to take the number of the thing that we're trying to convert to the other thing, like in this case hydrogen, 5.5. And I just have to remember divide by its coefficient and then multiply by the coefficient of the thing that I'm comparing it to. So in this case, 5.5 divided by the coefficient of hydrogen, which is 2, multiplied by the coefficient of oxygen, which is 1, and that gives me the same thing. It gives me that 2.8 that I got before. But if I have it set up in an ice chart, it's just really easy to just picture this math happening without having to write it out. And you're going to see us use that multiple times as we fill out the rest of the chart. But the green here just shows you this is nothing new. This is what you learned how to do last year. But the ice chart gives me a quick shortcut to be able to divide by its coefficient, multiply by the other coefficient in order to compare one amount to another using that mole-to-mole ratio. All right, so now I'm going to get that out of the way so it's not in our way, but because all we did was determine who was limiting. And now that I know who's limiting, there's a space on my ice chart that I immediately know the answer to, and that is I know that the end amount of oxygen has to be 0 because it's limiting, so I'm going to run out of it. And now that I have the end, I can determine that oxygen must have changed by negative 0.47 because it ended at 0 and started at 0.47. Now, the change is where the magic happens, is what I say. So once I know how much oxygen changed, because I have the balanced chemical equation, I know how much everybody else changed as well. So once you determine one of the changes, you can use it to find all of the changes. So right now, I know I used 0.47 moles of oxygen. Oh, and by the way, notice that it's negative because it's a reactant, and so the amount is going to go down. I can use that to determine how much hydrogen I used. And again, I use that shortcut I did before, which is just using the mole-to-mole ratio. I divide by its coefficient, which is 1, and then multiply by the coefficient of hydrogen, which is 2. So using up 0.47 moles of oxygen used up 0.94 moles of hydrogen. 0.47 divided by 1 times 2 gives you 0.94. So I immediately know that hydrogen, I started with 5.5, I used 0.94, and so now I know that I end up with 4.5 moles of hydrogen, which you can see is the last question I'm going to answer, right? It's going to help me get the mass of excess reactant. Well, while I'm here, I could have done the same thing with water, right? I could have taken oxygen's number, divided by 1, multiplied by 2, but I'm never going to do that. Because here's again, this is another real fast shortcut in ice charts. Everybody who has the same coefficient is going to have the same amount of change, right? If the coefficient of hydrogen is 2 and the coefficient of water is 2, for every 1 hydrogen I use, I make 1 water. And so as soon as I see that hydrogen has a change of negative 0.94, I know that water is going to increase by the same amount. So I can just do positive 0.94. Again, what I'm doing is I'm dividing by the coefficient of hydrogen 2 and multiplying by the coefficient of water 2. But if you divide by 2 and multiply by 2, you don't change anything. So again, everybody in the ice chart that has the same coefficient in the equation will have the same amount of change. Now, of course, in this case, it's positive because water is a product. So I'm going to make it. So I'm going to increase the amount of water. But I'm going to increase it by the same amount that hydrogen went down because they have the same coefficient in the equation, which is what the coefficients mean. So that means I end up with 0.94 moles of water. Now, because I wrote moles in the top left-hand corner of my ice chart, that reminds me all these numbers are in moles. And so now all that's left to get the final answer is to convert back to grams.
At this time, could we please have all...
Yes, so just in case you needed a reminder that I was actually still at school. So just convert back to mass, convert back to grams. So if we have 0.94 moles of water that were produced, I just used the molar mass of water to determine that means that I produced 17 grams of water. And then, of course, the mass of excess. I know hydrogen's what's excess since limiting was oxygen. 4.5 moles of hydrogen is simply 9 grams of hydrogen. So again, you could have done this without an ice chart, especially if it was only a one-part question. You might say it's much faster to do it without an ice chart. I would say, sure, that's true for now, but two things. Number one, once you get really good at ice charts, you can do them really fast. And I told my students, even when I'm working a multiple choice question on a college board exam, I'll oftentimes sketch a quick ice chart just because they become second nature and you can get a lot of information out of them. But then also, second semester, when we get into equilibrium, for example, you're going to have to do ice charts. And so it's going to be much easier to use ice charts with something brand new and unfamiliar like equilibrium if you've had some practice using them with what you already know how to do, like stoichiometry. So that's just an introduction to ice charts and how to use them to solve simple stoichiometry problems.